Hello. In this video we are going to look at yet another discrete random variable. This random variable is going to depend on time, however, which makes it a little different from the other discrete random variables that we have looked at thus far in this course. With all that in mind, the learning outcomes from this video are that by the end of it you should be able to explain what can be modelled using a Poisson process, and you should be able to write out the probability mass function for the Poisson random variable. Without further ado, let's get on to the real content of this video. In order to understand the Poisson process, let's begin by understanding a real-life manifestation of this particular random process. In this case, I would like you to imagine that you are sat beside a single-lane road, counting the number of cars that go past. Obviously, the times at which the cars pass is random, or at least subject to factors in their drivers' lives that you cannot possibly understand. The number of cars that have passed you at time t is thus a random variable. The fish, or Poisson, in the movie at the top of the slide, are illustrating this process of the cars driving past. The question that we would like to ask is how to simulate this random process. Well, one thing that we can do is that we can take the time interval over which we watch the road and we can divide it into segments of length delta. We then might observe the road for a while and note that lambda cars pass by on average every delta seconds. We can thus write that over 8 of these periods of length delta, we would expect 8 times lambda cars to pass by. Furthermore, if we want an expression for the fraction of the n time intervals in which a car drove past, we could write this fraction p as lambda times delta divided by n, the number of time intervals into which we have divided our total time window. Notice that we must multiply lambda, which is in units of time, to the -1, by delta, which is in units of time, in order to ensure that the final quantity p has no units as it should. The p that we extract in this way is the probability that we observe the passage of a car during a time window of length delta. Furthermore, as we have divided our time axis into n of these windows of length delta, we are essentially performing a series of Bernoulli trials. To be clear, we observe a success in the first of these trials if a car drives past during the first time window. We observe a success in the second of these trials if we observe a car drive past in the second time window, and so on. The result of all this is that because we observe the road for n of these time windows of length delta, what we are essentially sampling when we count the number of cars that go past over multiple time windows is a binomial random variable. We obtain the total number of cars that have passed us by performing a series of Bernoulli trials and by adding all these random variables together. Let's summarize all that was on the previous slide. We can model the number of cars that have passed by on the road at time T using a binomial random variable. To do this, we divide the time interval that we observe the road for into a series of segments. We then record a series of Bernoulli trials that tell us whether or not a car passed by during each of the n time intervals that we observe the road for. Furthermore, all of this is based on the fact that we observe lambda cars pass by on average over a period of length delta. Notice last of all that the time period delta we introduced now no longer needs to be the same as the length of the segments that we divide our time windows into. In other words, delta is not equal to the total time that we observed the rope for divided by n, the number of time intervals that we divided the observation time into. Delta is instead just a parameter of the particular model that we have generated. Delta could even be the total time that we observed the road for. We have thus shown that we can create a model for the number of cars that have passed by time t using a binomial random variable. The problem with doing things this way is that by doing it this way, we introduce a parameter, the number of segments into which we divided our observation time window. Ideally, we would like to avoid doing this, as we know that time is an infinitely divisible quantity that we would ideally like to treat as a continuous variable. What we would thus really like to do is divide the interval into an infinite number of segments. In other words, we would like to compute the limit of the binomial distribution as n tends to plus infinity. It turns out that computing this limit is rather straightforward, if we remember a few other standard limits. We first note that in the limit as n tends to infinity, n factorial over n minus x factorial is equal to n to the x. We can thus cancel these two terms in the expression as shown at the top of the slide. We next note that the limit as n tends to infinity of n minus x is equal to n. We can thus replace the exponent as shown here. Lastly, we recall the Euler definition of the exponential function that is shown here, which allows us to rewrite the second bracketed term in the above expression as e to the minus lambda times delta. The final result is that in the limit as n tends to infinity, the probability mass function for the binomial random variable reduces to the expression shown here. This final expression is the probability mass function for a new kind of random variable, a Poisson process. If we thus return to the question that we asked at the start of the video, namely how do we model the number of cars that have driven past us on a single lane road, we now have an answer. We can use a Poisson random variable. The probability mass function for this random variable is shown here. As you can see, the probability that the random variable, x of t, notice that this random variable depends on time, and that we're looking at the probability that this takes a value small x, is given by the expression shown here. Notice also that as t gets larger, the probabilities of having small x values of x that are small, decreases, and the probabilities of having values of x that are large increases as we would expect. Further notice that if we are interested in the probability that x of t equals 0, we find the following. We know that any number raised to the 0 is 1, and that 0 factorial is also 1. The probability that x of t is equal to 0 is thus e to the minus lambda t, which implies that the time until the first event is 1 minus e to the power minus lambda t, as shown here. This is just the cumulative probability distribution function for an exponential random variable, however. The time until the first event in a Poisson process is thus given by an exponential random variable. In fact, the time between any adjacent pair of events in a Poisson process is given by an exponential random variable, which, as we will see in the programming exercises, makes it rather straightforward to generate Poisson random variables. This concludes what I wanted to say about the Poisson random variable. Hopefully you are now able to explain what we can model using Poisson processes, and you have at least seen what the probability mass function for this type of random variable is. Now, you need to memorize this expression, as you will, once again, see this expression appear in many places when you start to use statistics to model time-dependent processes. Thank you for your attention.